Okay, I've been trying to get my next little fun thing for you posted. Um, I'm having trouble with the Python version and I'm blaming Python for it because one of the key um, ingredients to at least the Java implementation is exploiting the use of method overloading, which any reasonable object-oriented language supports, but Python, not being a reasonable object-oriented language, does not support. So, and that was causing some problems with implementing it for the Python folks. So after this class, I should have it fixed by at least before the lab starts. So don't worry. I know you've all been anxiously awaiting this. So anyway, but today we're going to continue with our look at the sensing piece. Are we on here? Okay. Let's stick to this. So what we've been kind of picking apart is this this detection sequence of things. In other words, the first step, of course, was modeling the fact that we can represent entities that move around, at least in a two-dimensional space. And just by the way, there's all of this stuff extends to 3D if you're, it just 3D just makes more complicated things. 3D is challenging to kind of at least display on a screen unless you have a whole bunch of other stuff. So, and interestingly, actually, I remember I've seen some interesting studies where they found that kind of comparing like 3D, using like 3D maps versus 2D maps, it turns out the 2D maps that people tend to be better using them than the other ones. So maybe it's just being used to it, but who knows? Anyway, so we're in 2D here. And so what we're looking at is we've already, with the, at least in the simplest version, looked at if we have one sensor and one target, that simplest referee business was able to handle the enter and exit range events. And just to kind of carry the thing all the way to the detections, in that simplest referee one, I had it schedule the detections, and several things were pointed out about this. One of which was that typically we want to have a more interesting way of modeling the detections. The other element, as was pointed out, that kind of having one of these for every interaction is is not a viable, scalable approach. And of course, there's a different one that's coming, but that will be next week. But we want to look at now, I mean, having done all that, what is it to model the time between these two events happen? So that's what we're looking at today. And and so to do that, I'll look at some implementations, but introduce another concept I call the mediator. So our simplest referee was one where we were listening for these change, what these events all are change of state, a change of movement state specifically. In other words, those equations for the enter and exit range are valid as long as the relative movement of the target and the sensor remain the same. In other words, as long as they're moving like that, and don't change anything, then all that computation is valid. So specifically, if we're in a situation where the target is totally missing it, then we don't have to spend another cycle of CPU worrying about that. We don't have to say, do you see me now, et cetera, et cetera. Now, just for those of you who are, there are probably some, if not all of you, are sort of thinking, well, I don't know, is this really going to work? And like a lot of things, it works in many situations, and it doesn't work so well in some others. Specifically, at least in my experience, when we're modeling movement in a typical scenario, units are not constantly changing their direction or in velocity. It's, and I remember like even in situations that you wouldn't think, I had a student who was looking at submarines and applying this kind of thing. So you think in a submarine, it would you would need kind of more, kind of a more nuanced approach to this. And so he was comparing this approach to a more detailed one, that where it was capturing the nuances of the submotion. And when he compared the trajectories, they were almost identical. Why? Because I mean, a sub isn't just going to be, kind of changing constantly. Now, now what's the situation where this kind of gets ground to a halt, where you, again, just imagine a lot of these things. If you're modeling a swarm of bees and you're modeling each individual bee, this is not ideal. Why? Because bees do change very rapidly. So because they're changing every time you're changing your movement state, you have to kind of cancel everything you did before and then redo everything like that. So a swarm of bees, this actually that does not scale to that. However, in realistic scenarios, it tends to work pretty well. Okay. So having said all that, in this, and this is actually kind of something relatively new, because in the actual methodology, the referee does not schedule these detections. So these detections here, this is really not part of the plan, because, well, hopefully we'll see. So this idea of the sensor listening to that, that's something that we're going to have to fix. But let's look at this additional issue of, we want to model detection following the interrange. And so the thing is that there's some time to detection. See, as I was haranguing the other day, in search and detection theory, the output of a lot of the analysis is called the probability of detection. And the thing is that in a simulation, that's kind of useless for two reasons. One is don't really care about the probability, and the second is that that's actually a somewhat ambiguous notion in a simulation. In other words, if I'm modeling something like this, and I'm going to tell you, okay, the probability that this sensor is going to detect the target is, let's say, 0.75. All right, how does that help me in figuring out where the sensor detects it? In other words, like if I'm doing let's say if I'm doing kind of like a defensive scenario where, let's say I have let's say incoming missiles, say, and I have countermeasures that I can do against them if I catch it in time. In other words, if I detect the target with enough lead time, I can launch a countermeasure and have a chance of destroying it before it actually hits me. But if I don't, then I'm not going to be able to get it in time. And you want this scenario to be able to capture that. So if all I give you is the probability of detection, that's not going to tell me whether I've detected it in enough time. In other words, the probability of detection is useless in a scenario like that. So what I want to know is, when do I detect it, and where is it when I detect it? That's what I want to know. And so I can know that in this scenario if I can capture, I'll call it TD, time to detection. So the time between when I could detect it and when I actually do detect it. And, you know, there are nearly infinitely many different ways of doing this. We're just going to look at it, the simple ones. So as you might imagine, I mean, I like to do things simple. So with that in mind, if I set my time of detection to 0, that's our cookie cutter sensor, you know, and we actually have a limitation to that with our simplest referee. But if, you know, what if I just have a constant time that's, say, bigger than 0? So in other words, the time between here, so the time between I enter here and when I actually detect it, it's just going to be some constant amount. Okay, now, is that the people who study this don't really talk about that? Why? Because it's not very interesting, because they want the probability of detection. But okay, but that's the next simplest thing. Again, as you might imagine, in my the way I like to do things is you start with the simplest and then step by step make it more complicated. So 0, the cookie cutter, that's the simplest. The next simpler is just make it a positive amount. And that's a little bit more realistic. And it's actually a little more realistic than you might imagine, because you think of, okay, like there's a certain fixed lag between when I start receiving pings and when I can kind of do it. Now, it's obviously not ideal, but it's better than the cookie cutter. Why? Because you see, the cookie cutter especially in defensive scenarios is the worst possible assumption, because what this is saying is that I'm always detecting my targets at the maximum possible range, and that always gives me the best you know, the best opportunity to conduct countermeasures, because I have the most amount of time to do that, always. And is that realistic? And I don't believe it is, you know, because it's like if the thing is coming in, you know, if I'm not detecting it in enough time to do the countermeasure, then I'm screwed. Okay, so and this captures that to a little bit. And then it turns out that, you know, the next most interesting thing is something where the time to detection is actually an exponential random variable with a certain mean. And I call that the constant rate because it has kind of an interesting motivation for this, which I'll kind of get to. But okay, but the point is here that, and then there are many more. I mean, I've had actually in some of my students, they've taken fairly sophisticated radar range equations and signal noise ratio types of things and applied this kind of thing. In other words, created ways of figuring out the time to detection that was strongly based in this case radar theory. So you can kind of go pretty deeply into this, and there are lots of these. Okay, but here's the modeling dilemma. You see, with our referee, you know, like who can do this? Well, if we put this on the referee, now we're going to have to really. I mean, it's actually sort of possible, but it requires a lot of complicated things that are really beyond the scope of this. In other words, if we reduce the referee's responsibility to just the enter and exit range guys, then that means that somebody else is going to have to kind of do this. And we want, you know, the ideal framework for this is one in which we can kind of plug and play these things fairly easily. And that's where the, you know, in other words, the detection events, they depend on which the rule that the sensor has. And so the idea is to have just it turns out all we need is just one object for each of the type of rule. In other words, if I have 50 sensors and they're all, let's say they're all one of these, then I only need one object to do it, and we'll see how that works. So the idea is that I call these mediators because they're going to hear the enter and exit range events from the referee, and then they'll schedule the detections or undetections as necessary. And then now, the other issue that comes up with this is, gets back to, okay, what do we do about this, this undetection thing? In other words, as depicted here, in principle, as long as the target is within our range, we could, in principle, kind of miss, it's like, okay, we see it, but then, okay, now we're not seeing it. Why? Because the things are kind of going on like that. So when it comes to modeling the detection, I mean, there is literally decades of theoretical research that you can tap into. I mean, even though I'm complaining about their output, I mean, there's a lot of theory that you can tap into as far as these goes. For example, there's an approach called glimpse models where you can kind of turn these pings into time. So all that's very well established. There's a lot of experimental data that sometimes goes into this. So for example, the Army, one of the models they like is called the Acquire algorithm. But it's based upon a lot of experimental data that they've done. It's overly complex in my view, but still it's got it's strongly rooted in experiments. So and that's what you want. There is a complete dearth of work, as far as I can tell, on how do you lose a target? In other words, how do you acquire a target? There's a lot of work on that. How do you lose a target? I mean, I haven't seen any. Now, if you have, I'd love to see it. But okay, so what do you do in that? What do we do in that case? So basically, what I'm in the absence of any theory, what I'm going to say is that if I've acquired a target, I'm going to keep acquiring it until I lose the range, and until there's some theory to suggest otherwise. That's what we're going to stick with. So in other words, what that means is we're going to schedule the undetections to coincide with the exit ranges, but there's kind of a placeholder for, so if the theory ever catches up to this, if anybody studies, okay, how do we, once we've acquired a target, how do we unacquire it? That's just sort of thing. Okay, so so the first thing is, as I said, the referee has no business scheduling the detections. And actually, you're, in the past, when I do this, we have to kind of wait until we do the mediators to actually get to the detections when we have implementation. I decided, okay, that was too much. I wanted to at least show the detections kind of happening and working with the sensor. So that's what. So we need to revise the referee though, and get rid of those things. So how can we do that? Well, the mechanism is, let's see, well, basically to subclass the simplest referee and override these two events. Yeah. So here's our simplest referee. Now I want to keep that around. So I'm going to subclass it. I'm to I call simplest referee 2. Heck, these days, every movie has a sequel. So, I just want to jump on the bandwagon. Okay, now remember that a bold border on an event means you're completely overriding. So we're completely overriding those scheduling of detections. But instead, what we're doing is we're scheduling an enter range event with the sensor and the target as its arguments. And likewise with the exit range, we're scheduling an exit range event with the sensor and the target as the arguments. And then since we want the enter range also schedule the exit range, if you remember, look at this. Well, actually it did. That was actually left out, but we need to actually do that. So now what's listening to it? A mediator. So a mediator, it's going to hear the enter range of the sensor and the mover and the exit range. And it's going to schedule the detection, on the sensor based upon the delay that that particular meter has done. And it's going to schedule the undetection with a delay of 0 because, and if there's ever any theory for this, then that would be put in the mediator as well. So if they say, well, we're losing the target at this particular rate or this particular time, then that would just be another parameter of the mediator. But just we're going to sort of stick. So now the 3 rules that we've discussed are the cookie cutter, where the time to detection is 0, the constant time where we have a positive amount of between that, and then the constant rate where it's actually, before I called it lambda, here I'm calling it mu. Just don't call it late for dinner. And now it's going to be an exponential random variable with a mean time to detection. Okay, so this is what every mediator is going to look like. And so we're going to have three, one class of mediator for each of these. And in this, if you can't tell from this, because we're passing the sensor and the target as arguments to the event, what that means is we don't need to have, one will do it for all. In other words, for every given mediator rule, we only need one mediator object. But we do need a different mediator class for each of the different rules. I mean, there's no getting around that. So what does the mediator do? It's going to hear this enter range with the right arguments from the, in this case, our revised referee. And it's going to schedule a detection with whatever its time to detection is. And it's going to pass the target as the argument. Okay, so now that's how this, and then the sensor, well, actually what it's going to be doing is it's going to be, and I haven't figured out a decent way of depicting this. What this is actually doing, it's scheduling this on the sensor itself, and we'll see that in the implementation. And so we could have the sensor just kind of listen to this. And that would sort of, the thing is that what we also kind of just peeking down the line a little bit, we want other objects to be potentially listening to these detection events, because we don't want the sensor to be kind of doing too much. But if we're having like a defense situation, or one in which say a mover that has a sensor on it needs to react to some detection, like let's say you're kind of traveling along and then you encounter a bad guy, and so what do? You might continue on your way, you might stop and retreat, or you might stop and engage the target. So again, that in order to do that, you would need to know about that detection, and so you need to be listening to the sensor. And so that's and so if the sensor only hears the event, the detection event, then it can't pass it to others. Now, the way you could pass it to others by having the detection schedule yet another event, but that it just seemed much more simple to put it on the sensor. Okay. Yes. Oh, yeah. Yeah. Yeah, it would be, yeah. Yeah. Well, you actually need both, as it turns out, because what can happen, and we haven't, is that like, let's say if the target does this and then does that, then when it does this turn, you're kind of you'd be canceling this one, but you wouldn't have another enter range because you're already in there. So that would be the situation where you have the one. So you actually need both. Yeah. So actually, the other situation is when you don't do that, when you just kind of go all the way through. Here all we have is the enter range event, and if you don't do anything else, this exit range doesn't get scheduled. Well, no, because the condition here is that we only have one positive root. You know, whereas at this point we had two positive roots. So, it's a good point. but yeah, it turns out we have to when we look at let's look at the implementation for just. I have that somewhere. All right, so oops, yeah, so I need to update. Okay, so so here's the overriding the simplest referee. You know, we have to redo our constructors. Now, remember in the superclass that we were, the censor was listening to the referee. We don't want that. And so we actually remove it here.
Sir, if you're sharing anything, we can't see it.
Oh, I'm not sharing. Thank you. Okay. That better? Thanks. Thanks for.
Yes, thank you.
Yeah, whenever I forget to share, let me know. Okay. And just just so you know, this is me doing hybrid mode 1.0. So with all of its, when you have the version 1, you have okay. That it's sort of weird. Okay, yeah. So I'm scheduling the enter range, and then scheduling the exit. Yeah, actually, I need to fix that a little bit, but because okay, yeah. So we're if remember the two routes were one was when we enter and the other is when we exit. So from the enter range event, the exit range is the second larger route. And then here we're scheduling the enter range with the censor and the target. We're using the getters because those are parameters. And in this case, unlike when we use a container for quote encapsulation purposes, we need to return a copy. But in this case, we need the actual object itself, and so we're not returning a copy. Otherwise, none of this would work. Okay, so that's all we need to do to fix that. All right. So now, as you can see, let's look at our cookie cutter mediator, and what it's doing is it has an enter range event that has an argument of a censor and a target. And all it does is it schedules a wait delay on the censor for detection passing the target. And likewise, the exit range is going to schedule an undetection with 0 delay and the target. And Now to test that, it's here. To test that, we're using the same scenario as before, except that now we have our mediator, and we simply have it listening to the referee. And we just need one of them, even no matter how many different, well, in this case, if we had different referees, the same mediator would listen to all the different referees. We don't need more mediators. And so when we run this, okay, you notice I didn't print the notice the mediator in this case has no parameters. So there's no point in, there's nothing to verify. So, but we have our sensor, our okay, so we have our 4 run events, and we're just sort of verifying that that all of these state transitions are kind of working. And so for our simplest path mover manager is really the first thing that happens. And it schedules the next waypoint, moves the index to 0, schedules a move to for the 50 minus 20. And then the move to just updates the destination and schedules a start move. And now that's going to be still heard by the referee. And so this is our start move time. Our velocity is working right, but now we have, notice, schedule range event from the simplest referee. And it turns out it schedules the enter range event. Okay, so now here's our enter range event, and here it's scheduling the enter range for but passing the sensor and the target. And also scheduling the exit range. So this is a case where it just goes shooting all the way through. And if the enter range didn't schedule the exit range, then there would be no exit range. So. Okay, so now here's the enter range of it. Then notice there's the detection from the simple sensor. So even though it's the mediator doing that, it looks like the sensor's doing it, and that's because it scheduled the wait delay on the sensor. And what that's going to enable other objects to hear that detection event. So we see that it updates the context correctly. That was the target it detected. And then in this case, notice that the exit range happens before the end move. So we do have the exit range. Okay, so this is the one in the referee, but this is the one that gets heard by the mediator, and it schedules the undetection. And then at the last end move, we have a schedule range, and then since we're at that point, we're just kind of outside everything. There's nothing to do. Okay, so now let's look at the next mediator, and that is the constant time one. And so it says between the enter range and the delay and the detection, there's just going to be some constant time. I'll call that delay time. It's just going to be a regular parameter now. And let's see, hopefully I remembered to, yeah, it had better be positive. Because if I want 0, I can just use the cookie cutter. So I want this to be positive. And so now when I hear an enter range with a sensor and a target, I schedule a detection, but my delay is the delay time. And I could use the getter or the variable itself, doesn't matter. But now there's actually kind of a little subtle thing about what to do with the exit range, because when there's a delay between, when there's no delay between entering the range and detection, then it's like they're detected immediately. But now I hear an exit range event, and there are 2 possibilities. Do you see what they are? Exactly. if because there's that delay, the target may have moved out of range before the detection actually kicked in. I mean, is that realistic? Sure. I mean, if you have a very fast moving target and you're kind of slow in getting it, is that something that could happen? Absolutely. Where it's like, okay, just never got it. You think of sort of radar and things like that. How does it responds to? It's trying to unravel both the noise and the signals that's getting back from it. And so if we have a very fast moving thing, it's like the signals you're getting never rise above the threshold in time, and the thing is out of range, and then you're not getting any pings whatsoever. Okay, so how can we on the other hand, if it has detected it, then we want to undetect it. That is, because the sensor is not allowed to hold on to the target forever, because once it's out, in other words, once it's out of range, then we don't have eyes on it anymore. Now we could apply some kind of dead reckoning, once it's out, and sort of guess where it is, and of course that decays over time. But that's a whole different thing. Once it's out of range, we don't have eyes on it anymore. So if we have, how can we tell whether we've detected? Well, if the sensor's contact contains the target, then we've detected it. And if it doesn't contain the target, then we need to cancel that detection that we had previously scheduled. So, and then this is sort of typical. In other words, mediators that have a delay more than 0, we've either detected it or not detected it, and you need both of those situations. So we can, oops, we don't need that. So basically kind of do the same here. I'll pick a delay. Oh, yeah. So now to test both of those, in this scenario, if I have a delay of 0.5, then I can test that the delay is actually working. So let's, what I'm looking for is the time between, so here's the enter range, and notice it's scheduled a detection at a later time, not the exact time. So now the detection occurs, and we have the exit range still happening, and then exit range occurs, and then we schedule the undetection. Then the undetection happens. We see that the sensor loses the target, and all that is carried on. However, if we have a longer delay, then we're going to be outside of the range before it happens, and so we want to make sure that's working. So we have here's our enter range, and then okay. So now notice that the detection is now is scheduled after the exit range. That's something that absolutely can happen. And so now the exit range. Okay, this is the exit range in the original one. And this is the one that's heard by the mediator. And so what we're looking for here, here's this detection. That exit range occurs, the detection is gone. Okay, so check. Okay, and then now this one I'm calling constant rate, and I don't have time to, maybe next week I'll kind of talk to why it's called constant rate. But if the idea is that we have our time to delay, our time between when we enter range and detect is going to be an exponential random variable with a given mean. Now, there are a couple ways of doing this. It turns out that we can exploit a property of the exponential distribution, which we will discuss in the module after this. We're going to peel back the hood on random variable generation, kind of what that's all about. And in the process, we'll be looking at some properties of, among other things, the exponential random variable, and you'll see why this kind of works. So now we have, now the exponential generator is, we could treat it as a parameter. And but we're not. Strictly, if we want to be strict about it, we would have a setter and getter. The thing is, we actually don't. The exponential generator, we want to only have a unit mean to detection, and we'll see what's happening with that. Because the delay that we're going to have is we're going to generate an exponential random variable with the mean of 1 and multiply it by the mean delay. And it turns out that that actually will give us an exponential random variable with the mean of whatever we've given it here. In general, you can't do that for every probability distribution. You can do for some of them, like the normal, but I mean, in general, this doesn't always work. It happens to work for the exponential. The alternative is we could actually set the distribution to this mean if we wanted. That would be an alternative. 6 to 1, half dozen to the other. Turns out this works. So our delay is going to be a random variable in this. Our undetection for the exit range is going to have the same issue because we now have a positive delay, and so we either detected it or not detected it. So similar type of thing here. So again, with the short delay, I want to make sure that both of these are working. And so when we kind of look at, okay, here's our enter range. And now notice that the detection is just some sort of weird distribute, you know, it's some weird, this is the generated value from that exponential. Even though it had the same mean, it was a random variable. So, and then here, exit range does the undetection. Okay, that works. And then it turns out for this, I had to crank up the mean delay to something like 5 to make sure that it was after the thing. So if I make it 5, the mean of 5, not the value of 5. And okay, so here's our enter range, and here the detection was after the exit range, as it turns out. So now our exit range occurs and then cancels the detection. Got to make sure both of those work. Okay, any questions about this? So this is all. Okay, so that's all I have for today. Now there is a Python implementation of this as well. And unfortunately the Python folk will have to watch another video that I'll do where I basically will walk through the same things that I've done for the Java, but in the Python one, so you can see how that works. So, and the lab will be posted sometime in the next hour or so. My apologies for that. I'm blaming it on Python. So it's never my fault.